Hello, dear friends. Am I audible? Please let me know if I'm audible. Okay. So, as per the request of one of the viewer, we are starting up with the reading of the second chapter, that is Work, Energy and Power. So, friends, tomorrow you have got your physics exam. So, 10th standard ICSE physics exam. And for this, we, on behalf of Intelletics, are trying to help you out maximum. So we shall be reading this. You just can keep plugged in on the way also towards your school. You can keep revising till the end minute. It certainly helps. Hi Arushi Shah. Hi Kundan Chan. Hi Sharon. Sharon, I had tried my level best even though there was a network glitch, technical glitch. I had floated up one paper. For you, I had especially typed out the paper even though it was late, and I felt very bad that I couldn't help you. So, Sharon, please stay hooked on. Okay, it's okay, Sharon. And whatever is your request, hak se bolo, that's not a problem. We will try our level best to help you out in the next last minute. Okay. So today, as per one suggestion that I got on the WhatsApp on the given number, okay, of our Intelletics, one viewer had given me a personal message saying that I don't know, he or she, I don't really recollect the name, feels very tired to read the entire thing, so would like me to read out the chapters. And this is the real reason why I have started this. After which, if time permits, I will solve three more papers that have been already scheduled. So you'll have to just keep hooked on. Okay. And if you can't, just tomorrow, if at all you're going to get up early in the morning, then you can go to the playlist and check out for the videos that have been live streamed. And Sharon, why don't you ask your friends also to join in? Ask as many friends as possible because everybody should be helped by this session. Okay, so here we start with first work, energy, and power, their measurements and units. We start with reading of 2.1, that is work. In our daily language, the word work is used for some sort of exertion, physical or mental, or for various activities such as while writing, reading, or eating. We say that we are doing work. But in physics, the term work is used in relation to the displacement produced by force. The work is said to be done only when a body moves under the influence of a force. If there is no displacement of the body, even when a force acts on it, the work done is said to be zero. Thus, work is said to be done only when the force applied on a body makes the body move. That is, there is a displacement of the body. Yes, Kundan Chand, you want me to do it for all the chapters, is it? That is what we are planning to. If you want, you can, hook on to the channel and keep listening and revising. Is that what you want, Kundan? Please reply. So this point gets very important. Please remember, work is said to be done only and only when the force applied on the body makes the body move. That is, there's a displacement of the body. For example, a man while pushing a cart, that is shown in figure 2.1, a cyclist while pedaling a cycle, a horse while pulling a cart, a boy going upstairs, a coolie lifting a load, all exert the force which produces motion, so they do work. However, if a man tries to push a wall, figure 2.2, or a child tries to push a heavy stone and they're unable to move it, then scientifically no work is being done by them. So please keep this in mind. If there is no motion, no work is done. Yes, Arushisha, we will certainly do it for all the chapters. Even Kundan wants the same. So just stay hooked on, logged on, okay? We will do it for you. Similarly, a coolie does no work while standing with a heavy load on his head, although he feels tired, since the displacement of the load is zero. Now let us understand how is work measured. That is, measurement of work. If forces F1 and F2 move two different bodies by the same distance, the work done by the force F1 is said to be more than that by the force F2. Similarly, for force F moves the body 1 and 2 by distances S1 and S2 respectively, where S1 is more than S2. The work done by the force F on the body 1 is said to be more than that on the body 2. Thus, the amount of work done depends on both the factors, the magnitude of the force applied and the magnitude of the displacement. So, the amount of work done by a force is equal to the product of the force and the displacement of the point of application of the force in the direction of the force. Very, very important point. The amount of work done by a force is equal to the product of the force and the displacement of the point of application of the force in the direction of the force. That is, work is equal to force into displacement of the point of application of force in the direction of force. Please look at the image 2.3 wherein there is work done by force. In figure 2.3, suppose a constant force F displaces a body from position A to position B along its own direction, then the displacement of the body is AB. That is equal to, let us say it is equal to S. And the work done, work is equal to F into S. Okay. So coming to the next expression. Here we assume that the force does not change during the displacement and it acts throughout the displacement. So in equation 2.1, if S is equal to 0, then W is equal to 0. Thus, if a force acts on a body and the body does not move, that is displacement is 0, when then no work is done. Work is a scalar quantity. Now let us understand about expression of work. That is expressed as W is equal to Fs cos theta. It is not necessary that the force always causes the displacement of the body in its own direction. If under some circumstances a force displaces the body in a direction other than the direction of the force, then we can determine the amount of work done by the force in two ways. First, by finding the component of displacement of the body in the direction of the force, and second, by finding the component of force in the direction of displacement. First, by finding the component of displacement along the force. So, in the figure 2.4, suppose a constant force F acts on a body along AB and displaces the body on an inclined surface from A to C. The displacement of the body is AC, that is equal to S, which is at an angle theta in the direction of the force. To find the component of displacement in the direction of force, that is along AB, a perpendicular CB is drawn from the point C on AB. Then the component of displacement in the direction of force is AB. Hence, work done W is equal to F into AB. So in equation 2.1, the sign x means simple multiplication of two scalars f and s which are the magnitudes of force and displacement respectively. It does not mean the cross or vector product of two vectors, that is F and S. But in right-angled triangle ABC, cos theta is equal to base upon hypotenuse, that is equal to AB upon AC is equal to AB upon S, or AB is equal to S cos theta. Hence, W is equal to F into S cos theta, or W is equal to force into component of displacement in the direction of force. Second, by finding the component of force along the displacement. In the figure 2.5, if PA represents the magnitude and the direction of the force acting on the body, then the component of force F in the direction of displacement, that is, along AC, is NA. Therefore, work done W is equal to NA into AC, that is equal to NA into S, but from right angle triangle PNA, NA is equal to PA cos theta, that is equal to F cos theta. Then work done W is equal to F cos theta into S, or work is equal to component of force in the direction of displacement into displacement. From equations 2.2 or 2.3, it is clear that the work done is equal to the product of first magnitude of force, second magnitude of displacement S, and third cosine of the angle theta between the directions of force and displacement S, that is cos theta. So note, since force F and displacement S are vector quantities and work W is a scalar quantity, so work is expressed as the dot product or scalar product of force and displacement vectors. The dot product of two vectors is a scalar. In vector form, work done W is written as W is equal to F dot S. Let us understand the special cases. Case 1. If the displacement is in the direction of force, that is theta is equal to 0 degrees, then cos 0 degrees is equal to 1. Therefore, work is equal to force into S. The work done is positive. Examples. First, in free fall of a body of mass m under gravity through a height h from A to B, that is figure 2.6, the force of gravity F is equal to mg is in the direction of displacement S, that is equal to h, and the work done by the force of gravity is W is equal to Fs, that is equal to mgh. So you can look at this particular figure wherein positive work done by the force of gravity in the free fall can be seen. Second example, a coolie does work on the load when he raises it up against the force of gravity. Both the force exerted by the coolie, that is equal to mg, and the displacement, that is equal to h, are in upward direction. The work done in raising the load is equal to mgh. Case 2. If the displacement is normal to the direction of the force, that is, theta is equal to 90 degrees, then cos 90 degrees is equal to 0. Therefore, work is equal to 0. Hence, the work done is 0. Examples. First, when a coolie walks on a horizontal ground while carrying a load on his head, no work is done against the force of gravity because the displacement of the load is normal to the direction of force of gravity, which is vertically downwards. Please remember, the coolie does work against the force of friction when he moves with the load. Second, when a body moves in a circular path in a horizontal plane, no work is done since the centripetal force on the body is directed towards the center of the circular path and the displacement at all instants is along the tangent to the circular path, that is, normal to the direction of force on the body as shown in the figure 2.7. It is for this reason that in a circular path, the kinetic energy and hence the speed of the body does not change although a force acts on the body. Further, on completion of one complete rotation, the total displacement of the body becomes zero. So the work done in one complete rotation is zero. Conditions for the work done by force to be zero. From this discussion, it is clear that the amount of work done by a force is zero in the following two situations. First, when there is no displacement, that is S is equal to 0. And second, when the displacement is normal to the direction of force, that is theta is equal to 90 degrees. Case 3. If the displacement is in a direction opposite to the force, that is theta is equal to 180 degrees, then cos 180 degrees is equal to minus 1. So W is equal to minus F into S. The work done is negative. This is usually the case when the force opposes the motion or it tries to stop a moving body. So case 3, if the displacement is in a direction opposite to the force, that is theta is equal to 180 degrees, then cos 180 degrees is equal to minus 1. Therefore, W is equal to minus F into S. The work done is negative. This is usually the case when the force opposes the motion or it tries to stop a moving body. Examples. First, when a body moves on a surface, the force of friction between the body and surface is in direction opposite to the motion of the body. Therefore, the work done by the force of friction is negative. Second example, when a ball of mass m is thrown upwards from A to B to a height h, figure 2.8, displacement h upwards is opposite to the direction of force of gravity mg, that is downwards. So the work done by the force of gravity mg in displacement h is W is equal to minus mgh, that is negative. So you can look at this image and understand this. This is a figure depicting the negative work done by the force of gravity in upward motion. Please remember, if the force is variable, that is, force varies during the displacement, the work done is determined by plotting a force displacement graph. The force is taken on y-axis and the displacement in the direction of force is taken on x-axis. The area enclosed by the sketch and the displacement axis, that is x-axis, gives the work done. In figure 2.9, the force F is directly proportional to the displacement and the graph of force against displacement is an inclined straight line OA. The work done by the force in displacement S is equal to the area of the triangle OAB, that is equal to half F into S, which is shown shaded in the figure 2.9. This method is applicable in all situations. If the force is constant, that is, it does not change with the displacement, the sketch on the graph will be a straight line parallel to the x-axis and the area of the rectangle enclosed between the straight line and the x-axis will be equal to the work done. Coming to the 2.3, work done by the force of gravity W is equal to mgh. Let a body of mass m be moved down through a vertical height h, either directly or through an inclined plane. Example, a hill, slope, or stairs. The force of gravity on the body is F is equal to mg, acting vertically downwards, and the vertical displacement in the direction of force is S is equal to h. Therefore, the work done by the force of gravity is W is equal to Fs, that is equal to mgh. Thus, work done by the force of gravity is same whether a person comes down from a certain height using the stairs, or slope, or a lift, or elevator. Similarly, if a boy of mass m goes up through a vertical height h, either directly or through the stairs, or slope, or lift, the work W is equal to minus mgh is done by the force of gravity on the boy, or the work W is equal to mgh is done by the boy against the force of gravity. Coming to the next, units of work. SI unit. The SI unit of work is joules. It is abbreviated as capital J. Since work is equal to force into displacement, therefore 1 joule is equal to 1 Newton into 1 meter. Thus, 1 joule of work is said to be done when a force of 1 Newton displaces a body through a distance of 1 meter in its own direction. Bigger units of work are kilojoule, megajoule, and gigajoule, where 1 kilojoule is equal to 10 raised to 3 joules, 1 megajoule is equal to 10 raised to 6 joules, and 1 gigajoule is equal to 10 raised to 9 joules. The Cgs unit. The Cgs unit of work is erg, where 1 erg is equal to 1 dyne into 1 centimeter. Thus, 1 erg of work is said to be done when a force of 1 dyne displaces a body through a distance of 1 centimeter in its own direction. Now let us understand the relationship between joule and erg. 1 joule is equal to 1 Newton into 1 meter, but 1 Newton is equal to 10 raised to 5 dynes and 1 meter is equal to 10 raised to 2 centimeters. Therefore, 1 joule is equal to 10 raised to 5 dynes into 10 raised to 2 centimeters. That is equal to 10 raised to 7 dynes into centimeters. That is 10 raised to 7 ergs. Remember, for stairs, h is equal to the number of stairs into height of each stair. Now, coming to the next, 1 joule is equal to 10 raised to 7 ergs. Students, please remember this relation. 1 joule is equal to 10 raised to 7 ergs. Now, coming to the next, that is 2.5 power. Power is equal to W upon T. Definition. The rate of doing work is called as power. Power is a scalar quantity. Now, let us understand the measurement of power. The power spent by a source is measured as the amount of work done per second by the source, or it is equal to the rate of doing work by the source. If work W is done in time t, then power P is equal to work done W upon time taken t, or P is equal to W by t. Thus, power spent by a source depends on the following two factors. First, the amount of work done by the source, and second, the time taken by the source to do the said work. If a machine or a person does a given amount of work in a less time, more power is spent by it, that is, or him. Example, if a coolie A takes 1 minute to lift a load to the roof of a bus, while another coolie B takes 2 minutes to lift the same load to the roof of the same bus, the work done by both the coolies is same, but the power spent by coolie A is twice the power spent by coolie B, because the coolie A does the work at double the rate, that is, in half the time. So note, if a constant force F acts on a body and it displaces the body by a distance s in the direction of the force in time t, then work done W is equal to F into s. Remember this, W is equal to F into s. And power P is equal to W upon T, that is equal to F into s upon T. But s upon T is equal to V, that is average speed. Therefore, power is equal to force into average speed, or P is equal to F into V. This relation is very, important, friends. You will have to keep these things in mind because this can be asked to you anytime. Now, coming to the next, that is units of power. SI unit. The SI unit of power is watt. It is abbreviated as capital W. So if 1 joule of work is done in 1 second, the power spent is said to be 1 watt. That is, 1 watt is equal to 1 joule upon 1 second. That is equal to 1 joule per second. Bigger units of power are kilowatt, megawatt and gigawatt, where 1 kilowatt is equal to 10 raised to 3 watts, 1 megawatt is equal to 10 raised to 6 watts, and 1 gigawatt is equal to 10 raised to 9 watts. Smaller units of power are milliwatt and microwatt, where 1 milliwatt is equal to 10 raised to minus 3 watts and 1 microwatt is equal to 10 raised to minus 6 watts. Coming to the C.G.S. unit. The C.G.S. unit of power is erg per second. That is erg per second. Relationship between the SI unit and C.G.S. unit. 1 watt is equal to 1 joule per second. That is equal to 10 raised to 7 ergs per second. Coming to another thing, that is horsepower. It is another unit of power, largely used in mechanical engineering. It is related to the SI unit watt as below. 1 horsepower is equal to 746 watts. That is equal to 0.746 kilowatts. Very, very important. They can ask you 1 horsepower is equal to dash. Now coming to the difference between work and power. Work done by a force is equal to the product of force and the displacement in the direction of the force, whereas power of a source is the rate of doing the work by it. Second, work done does not depend on time, whereas the power spent depends on the time in which work is done. Third, SI unit of work is joules, whereas SI unit of power is watt. Now, coming to the next, that is energy. Energy as work done. A body capable of doing work is said to possess energy. The energy possessed by a body is measured by the amount of work that a body can perform. When a body does work, its energy decreases, while if work is done on the body, its energy increases. It means that whenever work is done, there is always a transfer of energy. Remember this, whenever work is done, there is always a transfer of energy. Thus, energy and work are related to each other. We can define energy as the energy of a body is its capacity to do work. Like work, energy is also a scalar quantity. Remember this, energy is also a scalar quantity. Coming to the next, units of energy. The units of energy are same as that of work. First, the SI unit of energy is joule and the C.G.S. unit of energy is erg, where 1 joule is equal to 10 raised to 7 ergs. Second, the bigger units of energy are watt hour and kilowatt hour. Now, first one, watt hour. 1 watt hour, that is 1 capital W small h, is the energy spent or work done by a source of power 1 watt in 1 hour. That is 1 watt hour is equal to 1 watt into 1 hour. That is equal to 1 joule per second into 3600 seconds. That is equal to 3600 joules. That is equal to 3.6 kilojoules. Please keep this in mind. Kilowatt hour. 1 kilowatt hour, that is 1 kWh, is the energy spent or the work done by source of power, that is 1 kilowatts in 1 hour. That is 1 kilowatt hour is equal to 1 kilowatt into 1 hour. That is equal to 1000 joules per second into 3600 seconds. That is equal to 3.6 into 10 raised to 6 joules. That is equal to 3.6 megajoules. Please remember, watt and kilowatts are the units of power, while watt hour and kilowatt hour are the units of work or energy since power into time is equal to work or energy. Coming to the next, calories. Heat energy is usually measured in calories. 1 calorie is the energy or the heat required in raising the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade or through 1 degree Celsius. It is related to joule as 1 joule is equal to 0.24 calories or 1 calorie is equal to 4.18 joule. Kilocalorie is a bigger unit of heat energy. 1 kilocalorie is equal to 1000 calories, that is equal to 4180 joules. Coming to the next, that is electron volts. The energy of atomic particles is very small, so it is measured in electron volt. 1 electron volt is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. That is, 1 electron volt is equal to charge on an electron into 1 volt. That is equal to 1.6 into 10 raised to minus 19 coulombs into 1 volt. That is equal to 1.6 into 10 raised to minus 19 joules. Or 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. Now let's understand the difference between energy and power. Energy of a body is its capacity to do work, whereas power of a source is the rate at which energy is supplied by it. Second, energy spent does not depend on time, whereas the power depends on the time in which energy is spent. SI unit of energy is joule, whereas SI unit of power is watt. Now, these are the examples that have been solved in the textbook. You will have to actually try solving it. So, coming to the next. So, exercise questions. I hope by now you might have already solved it. We go ahead. So, let's come to the B part of the chapter, that is different forms of energy. To start with, the mechanical energy and its different forms. The energy possessed by a body due to its state of rest or of motion is called the mechanical energy. It is in two forms. First, potential energy, and second, kinetic energy. The total mechanical energy of a body is equal to the sum of its potential energy and kinetic energy. Potential energy U. The energy possessed by a body by virtue of its changed position or configuration is called as the potential energy. It is usually denoted by the symbol capital U. Examples: a body placed at a height above the ground, a wound quartz spring, a compressed spring, a bent bow, a stretched rubber string, etc. have the potential energy. Forms of potential energy. In mechanics, potential energy is mainly of two kinds. First, gravitational potential energy due to its changed position, and second, elastic potential energy due to its changed configuration. First, gravitational potential energy. The potential energy possessed by a body due to force of attraction of Earth on it is called its gravitational potential energy. The gravitational potential energy of a body is zero when it is at infinity, because the force of attraction of Earth on the body is then zero. Please keep this in mind. The gravitational potential energy of a body is zero when it is at infinity, because the force of attraction of the Earth on the body is then zero. At a finite distance from Earth, the gravitational potential energy of the body is negative. As the distance of the body from the surface of the earth increases, the force of attraction of the earth decreases and its gravitational potential energy increases. That is, the negative value of gravitational potential energy decreases. The gravitational potential energy of a body at a point is the amount of work done by the force of attraction of the earth in bringing that body from infinity to that point. Coming to the second, that is elastic potential energy. When an external force is applied on a body, its configuration or shape changes. Elasticity is the property by virtue of which a body regains its original configuration on removal of the external force. The potential energy possessed by a body in the deformed state due to change in its configuration is called the elastic potential energy. It is equal to the amount of work done in deforming the body or in changing the configuration of the body. Coming to the next, that is gravitational potential energy at a height, U is equal to mgh. The gravitational potential energy of a body at a height above the ground is measured by the amount of work done in lifting it up from the ground to that height against the force of gravity, assuming that its gravitational potential energy on the ground is zero. Let a body of mass m be lifted from the ground or the earth's surface to vertical height h. The least upward force F required to lift the body without acceleration must be equal to the force of gravity, that is equal to mg, on the body acting vertically downwards. The work done W on the body in lifting it to a height h is W is equal to force of gravity, that is mg, into displacement h, that is equal to mgh. This work is done in lifting the body up and it gets stored in the body in the form of its gravitational potential energy when it is at height h. Thus, gravitational potential energy U is equal to mgh. Precisely, mgh is the gain in potential energy of the body when it is raised to a height h above the ground. But here we have assumed that when the body is on the Earth's surface or ground, its gravitational potential energy is zero. So we consider the gravitational potential energy of the body at height h equal to mgh. Thus, when a body is thrown vertically upwards, it rises up. So the height of the body from the ground increases. Hence, its potential energy increases. Similarly, when the body is released from a height, it falls down. So the height of the body from the ground decreases. Hence, its potential energy decreases and it becomes zero at the Earth's surface. When a body of mass m is taken up from a height h1 to a height h2 above the ground, wherein h2 is more than h1, the gain in potential energy is equal to final potential energy minus initial potential energy, that is equal to mg into brackets h2 minus h1. But if a body of mass m falls down from a height h1 to a height h2 above the ground, wherein h2 is lesser than h1, the loss in potential energy is equal to initial potential energy minus final potential energy, that is equal to mg into bracket h1 minus h2. Now coming to the next, that is kinetic energy. The energy possessed by a body by virtue of its state of motion is called as kinetic energy. It is usually denoted by the symbol K. Examples: a fast moving stone has the capacity of breaking a window pane on striking it, and thus it has a kinetic energy. Similarly, a car in motion, moving hands of a clock, the bullet fired from a gun, a rolling ball, an apple falling from a height, etc., have the kinetic energy. Expression for the kinetic energy K is equal to half mv squared. The kinetic energy possessed by a moving body is equal to the amount of work which the moving body can perform before coming to rest. It can be calculated by the amount of work done by an opposing force to stop the body. Suppose a body of mass m is moving with a velocity v. It is brought to rest by applying the constant opposing force F. Let A be the uniform retardation produced by the force, and the body travels a distance s before coming to rest. Then, retarding force F is equal to mass into retardation, that is equal to mass m into A. Kinetic energy of the body is equal to work done by the retarding force in stopping it, or kinetic energy K is equal to retarding force into displacement, or K is equal to F into S. Now, to calculate the displacement S, we have initial velocity U is equal to V and final velocity V is equal to 0. Since A is the retardation, so acceleration is equal to minus A. From the relation, V square is equal to U square plus 2AS. So 0 is equal to V square minus 2AS. Therefore, displacement S is equal to V square upon 2A. So substituting the values of F and S from the equations 1 and 3. The equation 2 that we get is kinetic energy K is equal to F into S. That is equal to MA into V square upon 2A, that is equal to half MV square. So K is equal to half mv square. Kinetic energy is equal to half mass into velocity square. The relationship between kinetic energy and momentum. Let a body of mass m be moving with the velocity v. Then its kinetic energy K is equal to half mv square. So momentum P is equal to mv. Substituting the value of V is equal to PLM from equation 2 in equation 1, we get K is equal to half M into brackets P upon M the whole square, that is equal to P square upon 2M, or P square is equal to 2MK. Thus kinetic energy K and momentum P are related as P is equal to under root of 2MK, or K is equal to P square upon 2M. Very, very important relation. Please keep this in mind. Now coming to the next, work energy theorem. When a force is applied in the direction of motion of a body, it accelerates the motion and thus increases the kinetic energy of the body. This increase in kinetic energy is equal to the work done by the force on the body. This is called the work energy theorem. Thus, according to the work energy theorem, the work done by a force on a moving body is equal to the increase in its kinetic energy. Let a body of mass m be moving with an initial velocity u. When a constant force F is applied to the body along its direction of motion, it produces an acceleration A, and the velocity of the body changes from u to v in moving a distance s. Then force F is equal to mass into acceleration, that is equal to mk. F is equal to ma. पता है हम बचपन में हम लोग एक सर थे जो हमें ये चीज याद दिलाते थे. F for father. Father is equal to mother, mom. Easy to remember. Work done by the force is equal to force into displacement, or W is equal to F into S. From relation, V squared is equal to U squared plus 2AS. Displacement S is equal to V squared minus U squared upon 2A. Substituting the values of F and S from equations. W is equal to MA into brackets V square minus U square upon 2A. That is equal to half M into brackets V square minus U square. Or W is equal to half mv square minus half mu square. But initial kinetic energy Ki is equal to half mu square and final kinetic energy Kf is equal to half mv square. Then from equation 2.16, work done on the body W is equal to Kf minus Ki, increase in the kinetic energy. Then let's understand the forms of kinetic energy. A body can have three types of motion, namely the translational, rotational, and vibrational. So the kinetic energy is also of three forms. That is translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. First, translational kinetic energy. The motion of a body in a straight line path is called the translational motion, and the kinetic energy of the body due to motion in a straight line is called as the translational kinetic energy. Examples: a car moving in a straight path, a freely falling body, a molecule of monoatomic gas have the translational kinetic energy. Second, rotational kinetic energy. If a body rotates about an axis, the motion is called the rotational motion, and the kinetic energy of the body due to rotational motion is called the rotational kinetic energy, or simply the rotational energy. Examples: a spinning top, a rotating wheel have the rotational kinetic energy. The Earth rotating on its own axis has a huge amount of rotational kinetic energy. The atoms in a diatomic or polyatomic molecule rotate about a fixed axis in addition to their translational motion. So they possess both the rotational and translational kinetic energies. Third, vibrational kinetic energy. If a body moves to and fro about its mean position, the motion is called as a vibrational motion. The kinetic energy of the body due to its vibrational motion is called the vibrational kinetic energy, or simply the vibrational energy. Examples: a wire clamped at both the ends. When stuck in the middle, it vibrates. The energy possessed by the wire is the vibrational kinetic energy. A steel strip clamped at one end vibrates when the other free end is displaced slightly and then released. The steel strip is then said to possess the vibrational kinetic energy. In a solid, the atoms vibrate about their mean positions, and so they possess the vibrational kinetic energy. In a polyatomic molecule, the atoms can vibrate about their mean positions, so a polyatomic molecule has a vibrational energy in addition to the rotational and translational energies. Remember, a molecule with two or more than two atoms such as H2, O2, N2, HCl, H2O, NH3, etc. is called as a polyatomic molecule. Remember, depending upon its state of motion, a moving body may possess either one or more than one form of kinetic energy simultaneously. Very, very important point. Depending on its state of motion, a moving body may possess either one or more than one form of kinetic energy simultaneously. For example, a rolling ball and the wheel of a running vehicle. For example, a rolling ball and the wheel of a running vehicle have both the translational and rotational kinetic energies simultaneously. Now let us understand the difference between the potential energy and the kinetic energy. Potential energy. It is the energy possessed by a body due to its changed position or configuration, whereas kinetic energy is the energy possessed by a body due to its state of motion. Potential energy is equal to the work done in bringing the body to its changed state, whereas kinetic energy is equal to the work that a moving body can do before coming to rest. Potential energy can change only in the form of kinetic energy, whereas kinetic energy can change into any other form. Potential energy does not depend on the speed of the body, whereas kinetic energy depends on the speed of the body. Coming to the next, that is conversion of potential energy into the kinetic energy. Potential energy changes into the kinetic energy whenever it is put to use. Examples first. A stone at a height has gravitational potential energy due to its raised position. When the stone is made to fall on a nail standing on a wooden piece, the nail begins to penetrate. The reason is that as the stone starts falling, its potential energy begins to change into kinetic energy. The falling stone now has kinetic energy. When it strikes the nail, the kinetic energy of the stone works on the nail. The kinetic energy of the stone changes into the kinetic energy of the nail, due to which the nail moves into the wooden piece. Second example, a wound up watch spring has elastic potential energy because of its wound up state. As the spring unwinds itself, the potential energy stored in it changes into the kinetic energy, which does work in moving the hands of the watch and thus changes into the kinetic energy of the hands. Kundan Chand, this was what you wanted to know. This is what it is. I hope you did. Did you understand? Coming to the third example, when the string of a bow is pulled, some work is done which is stored in the deformed state of the bow in the form of its elastic potential energy. On releasing the string to shoot an arrow, the potential energy of the bow changes into the kinetic energy of the arrow, which makes it move. Coming to the fourth example, a compressed spring has elastic potential energy due to its compressed state. When it is released, the potential energy of the spring changes into the kinetic energy, which does work on the ball placed on it and changes into the kinetic energy of the ball, due to which it flies away. You can definitely see this image for you to understand it better. कुंदन आपको समझ में आ गया? कुंदन चांद बच्चा आप हो? Please reply if you understood it. Need motivation. बच्चा आपके पेपर में आपने कैपिटल लेटर में लिखा है तो आई डोंट थिंक कि दैट शुड बी अ रीजन फॉर योर मार्क्स टू बी डिडक्टेड. आप शांत रहे. डोंट वरी बच्चा, टीचर्स इतने भी खड़ूस नहीं होते, थोड़े से ही होते. Now coming to the next different forms of energy. Nature has provided us energy in the various forms, namely, first, solar energy, second, heat or radiant energy, third, light energy, fourth, chemical or fuel energy, fifth, hydro energy, sixth, electrical energy, seventh, nuclear energy, eighth, geothermal energy, ninth, wind energy, 10th, sound energy, 11, magnetic energy, and 12, mechanical energy, etc. These forms of energy are described. The first one is the solar energy. The energy radiated out by the sun is called the solar energy. Solar energy cannot be put to work directly because it is too diffused and it is not always available uniformly. A very, very important point. Why can't you use the solar energy for working directly? First, because it is in the diffuse state, and second, it is always not available uniformly. Please keep this in mind. However, a number of devices such as solar panels, solar furnaces, and solar cells, etc., have been invented to make the use of solar energy. A solar panel consists of black painted metal surface which absorbs the sun's energy and heats the water in its contact. Second, in a solar furnace, parabolic mirror is used. This is important. I can ask you what kind of mirror is used in the solar furnace. Please remember it is a parabolic mirror. So in a solar furnace, parabolic mirror is used to focus the sun rays on a small area so that a high temperature is achieved. Thus, by keeping water at the focus of the mirror, water can be boiled to produce steam, and steam can then be used to drive the turbines of an electric generator so as to obtain the electrical energy. Third, the solar cells are used to convert the solar energy directly into the electrical energy. These cells are made from thin slices of semiconducting material. However, the efficiency of a solar cell to convert solar energy into electrical energy is very low. Second, heat energy. The energy released on burning coal, oil, wood, or gas is heat energy. The steam obtained on heating water possesses heat energy and it has the capacity to do work. In a steam engine, heat energy of the steam is used to obtain work, that is mechanical energy. We receive heat energy on Earth directly from the sun. Third, light energy. It is a form of energy in presence of which other objects are seen. The natural source of light energy is sun. The moon reflects the sunlight at night. Many sources, such as fire, burning candle, etc., also give light energy along with the heat energy. Fourth, chemical or fuel energy. The energy possessed by the fossil fuels, such as coal, petroleum, and natural gas, is called the chemical energy or fuel energy. These fuels contain chemical energy stored in them. When fuels are burnt, the chemical energy changes into the heat and light energy. The food that we eat also has a chemical energy in it. Plants convert the solar energy into chemical energy of food during the process of photosynthesis. A battery has chemical energy stored in it and it provides the electrical energy when in use by a chemical reaction which takes place in it. Hydro energy, as the term tells you, hydro. The word hydro always is used in terms or in connection with water. So when we say hydro energy, it is energy possessed by the fast moving water, and that is called as hydro energy. This energy is used to generate electricity in the hydroelectric power stations. For this, water is stored in the dams built across the rivers high up in the hills, and the water in the dams is allowed to fall down through pipes. The kinetic energy of the falling water drives the turbines of the generators, which produces electrical energy. Coming to the sixth, electrical energy. When two dry bodies are rubbed together, they get charged due to the movement of the free electrons from one body to the other body. So they possess electrical energy. An electrical cell is a source of electrical energy due to movement of ions from one electron to the other electrode within the cell as a result of chemical reaction. Seventh, nuclear energy. The energy released due to loss in mass during the processes of fission and fusion is called the nuclear or atomic energy. In both these processes, the loss in mass gets converted into energy in accordance with the Einstein's mass energy relation, that is E is equal to mc squared. This energy is used in the nuclear reactors for the constructive purpose to produce electrical energy and is used in atom bombs for the destructive purpose to produce heat and other forms of energy so as to destroy the enemy in the war. Yes, Kundan Chand, after this chapter, definitely we shall try for light. Don't worry. I just want you to hook on with all your friends. Can you please spread a word about this channel to your friends? This will certainly help you better. Point number 8, geothermal energy. The energy released in nuclear disintegrations in the interior of the Earth gets stored deep inside the Earth and is called as the geothermal energy. This energy heats up the underground water to produce the natural steam. Sometimes the natural steam may burst out from the surface of the Earth as hot springs. The electric power companies may drill wells into the earth to trap the natural steam, which may be used to run the turbines or generators to produce electricity. Ninth form, that is wind energy. The energy possessed by the fast moving air, that is storm, is called as wind energy. This energy is used in driving a windmill. In past, for many years in rural areas, windmills were used to pump out the underground water and to grind the grains. Nowadays, large giant windmills are being used to drive the turbines of electric generators for producing electricity. 10th is sound energy. A vibrating body possesses the sound energy. It is sensed by our ears. When the disturbance produced by a vibrating body in the atmospheric air layers reach our ears and produce vibrations in the ear membrane, sound is heard. 11th, magnetic energy. The energy possessed by a magnet due to which it can attract iron filings is called the magnetic energy. An electromagnet has the magnetic energy. 12th, mechanical energy. The energy possessed by a body due to its state of rest or of motion is called the mechanical energy. A body at a height, a moving body, a stretched bow, etc. have the mechanical energy. Coming to the next, 2.15, that is conversion of one form of energy into other form. In our daily life, we require energy in various forms. Since one form of energy can be converted into the other form, we can obtain the energy in the required form from the form of energy available to us. Figure 2.11 shows some examples of conversion of energy from one form to the other form. Now, we consider below some more examples of conversion of one form of energy into the other form. First, mechanical energy into electrical energy. The water stored in the reservoir of a dam has a potential energy. When the water falls, its potential energy decreases and kinetic energy increases. If the falling water is made to rotate a turbine near the bottom of the dam, the kinetic energy of the water is transferred to the turbine in the form of rotational kinetic energy, due to which it rotates. The turbine rotates the armature of the generator connected to it, and thus the kinetic energy gets transformed into the electric energy in the generator. Thus, an electric generator or a dynamo converts the mechanical energy into electrical energy. You can look at this particular image to understand the examples of energy conversion. Going ahead, electrical energy into mechanical energy. In an electric motor, when an electric current is passed in a coil freely, suspended or pivoted in a magnetic field, a torque acts on the coil due to which it rotates. The shaft attached to the coil also rotates with it. Thus, the electrical energy changes into the mechanical energy. The electric motor is used in many home appliances such as electric fan, washing machine, mixer, grinder, etc. It is also used to run the industrial machines. Third, electric energy to heat energy. In electric appliances such as heater, oven, geyser, toaster, etc., electrical energy changes into the heat energy when a current passes through their resistance wire or filament. Fourth, heat energy to electrical energy. In a thermocouple, when two junctions of two different metals are kept at different temperatures, one junction is kept hot while the other cold. A current flows in the thermocouple. Thus, a thermocouple changes the heat energy supplied at the hot junction into the electrical energy. Fifth, electrical energy to sound energy. A loudspeaker, when in use, receives electrical energy in the form of electrical signals from the microphone and changes it into the sound energy. In an electric bell, when an electric current is passed, the electrical energy changes into the sound energy. Sixth, sound energy into electrical energy. A microphone converts the sound energy into the electrical energy in the form of varying electric signals. Seventh, electrical energy into chemical energy. While charging a battery, the electrical energy changes into the chemical energy of the cell. Eighth, chemical energy into electrical energy. From an electric cell, when current is drawn, the chemical energy stored in it changes into the electrical energy. Ninth, chemical energy to light energy. When a candle burns, it gives light. Similarly, in a kerosene lamp, when the oil soaked in its wick burns, the chemical energy changes into the light energy. 10th, light energy to chemical energy. The light energy from the sun is absorbed by the green plants and they change it in the form of chemical energy during the process of photosynthesis. 11th, electrical energy into light energy. When an electric bulb glows on passing an electric current through it, the electrical energy changes into the heat and light energies. 12th, light energy to electrical energy. In a photoelectric cell, the light energy gets converted into the electrical energy. In a solar cell, the light or solar energy changes into the electrical energy. Manveer Singh Sandhu, can you please elaborate on what exactly do you want me to tell you about? 13th, heat energy to mechanical energy. In a steam engine, the chemical energy of the coal first changes to heat energy of the steam, and then heat energy of the steam changes into the mechanical energy. 14th, chemical energy to heat energy. When fuel such as wood, coal, biogas, etc. burns, the chemical energy changes into the heat energy. In explosion of crackers, the chemical energy changes into the heat, light, and sound energies. In lighting a candle or matchstick, the chemical energy changes into the heat and light energies. In respiration, the chemical energy converts into the heat energy. 15th, chemical energy to mechanical energy. In automobiles, while in motion, the chemical energy of petrol or diesel changes into mechanical energy or kinetic energy. 16th, electrical energy to magnetic energy. While making an electromagnet, an electric current is passed in a coil wound around a soft iron bar, which gets magnetized. Thus, the electrical energy changes into magnetic energy. 17. Mechanical energy to heat energy. When water falls from a height, the potential energy stored in water at that height changes into the kinetic energy of water during the fall. On striking the ground or bottom, a part of the kinetic energy of water changes into heat energy, due to which the temperature of water rises. The moving parts of a machine gets heated due to friction. Thus, a part of mechanical energy changes into heat energy. Please remember, first, whenever mechanical energy changes to other forms, it is always in the form of kinetic energy and not in the form of potential energy. That is, the stored potential energy first always changes to kinetic energy and then kinetic energy changes to other form. Second, remember that while transformation of energy from one form to the other desired form, the entire energy does not change into the desired form, but a part of it changes either to some other undesirable form, usually heat, due to friction, or a part is lost to the surroundings due to radiation, which is not useful. This conversion of energy to the undesirable or non-useful form is called as the dissipation of energy. Since this part of energy is not available to us for any productive purpose, so we call this energy as the degraded form of energy. Now, I suppose these examples, you might have solved them. Now, it's too late to ask you this, but still, you can always have a quick look at it, especially the formulae, because they can ask you numericals in the form of MCQs. So you have to be well prepared with it. Now we come to the C part of the chapter, that is conservation of energy. So let's talk about the principle of conservation of energy. According to the principle of conservation of energy, energy can neither be created nor can it be destroyed. It only changes from one form to another. In universe, energy occurs in various forms. The sum of all forms of energy in the universe remains constant. When there is a transformation of energy from one form to another, the total energy always remains same. That is, it remains conserved. If there is only an interchange between the potential energy and kinetic energy, the total mechanical energy, that is, the sum of kinetic energy K and the potential energy U, remains constant. That is, K plus U is equal to constant when there are no frictional forces. The principle of conservation of energy is one of the fundamental principles of nature. Theoretical verification of K plus U is equal to constant for freely falling body. So let's understand this. Let a body of mass m be falling freely under gravity from a height h above the ground, that is, from position A in the figure to point 50. As the body falls down, its potential energy changes into the kinetic energy. At each point of motion, the sum of potential energy and kinetic energy remains unchanged. To verify it, let us calculate the sum of kinetic energy K and potential energy U at various positions, say at A at a height h above the ground, at B when it has fallen through a distance x, and at C, that is on the ground. So please look at this figure. At the position A, at height h above the ground, initial velocity of the body is equal to 0, since body is at rest at A. Therefore, kinetic energy K is equal to 0. Potential energy U is equal to mgh. Hence, total energy is equal to K plus U is equal to 0 plus mgh, that is equal to mgh. At the position B, when it has fallen a distance x, let v1 be the velocity acquired by the body at B after falling through a distance x. Then u is equal to 0, s is equal to x, a is equal to g. From the equation, v square is equal to u square plus 2as. That is, v1 square is equal to 0 plus 2gx, that is equal to 2gx. Therefore, kinetic energy K is equal to half mv1 square, that is equal to half m into 2gx, that is equal to mgx. Now at B, height of the body above the ground is equal to h minus x. Therefore, potential energy U is equal to mg into brackets h minus x. Hence, total energy is equal to K plus U, that is equal to mgx plus mg into brackets h minus x is equal to mgh. Now, at the position C on the ground, let the velocity acquired by the body on reaching the ground be v. Then u is equal to 0, s is equal to h, a is equal to g. From equation, v square is equal to u square plus 2as. V square is equal to 0 plus 2gh, or v square is equal to 2gh, or kinetic energy K is equal to half mv square, that is equal to half m into 2gh, that is equal to mgh. And potential energy U is equal to 0 at the ground when h is equal to 0. Hence, total energy is equal to K plus U, that is equal to mgh plus 0, that is equal to mgh. Thus, from equations 1, 2 and 3, we note that the total mechanical energy, that is the sum of kinetic energy and potential energy, always remains constant at each point of motion, and it is equal to the initial potential energy at height h. As the body falls, its potential energy decreases and kinetic energy increases. The potential energy changes into kinetic energy. Just at the instant when it strikes the ground, the whole of the potential energy has changed into the kinetic energy. Therefore, the kinetic energy of the body on reaching the ground is equal to the initial potential energy at height h. Similarly, when a body is thrown vertically upwards under gravity, its initial kinetic energy supplied at the instant of throwing up keeps on decreasing and the potential energy keeps on increasing by the same amount. When the body reaches the highest point, whole of its initial kinetic energy has changed into the potential energy, and therefore the body momentarily comes to rest. At this instant, the body is still under the influence of the force of gravity, so the body starts falling down and its potential energy begins to change into the kinetic energy. Please remember the initial kinetic energy provided to the body at the ground so as to reach a certain height h must be equal to the potential energy of the body at that height h, that is equal to mgh. Thus, the initial velocity v to be imparted to the body so as to reach a height h is given as half mu square is equal to mgh, or u is equal to under root of 2gh. प्रेम साहू बाकी के 5 चैप्टर्स कंप्लीट कर दीजिए प्लीज. डेफिनेटली बच्चा, आप चैनल पे जुड़े रहिए. हम आज करेंगे ही करेंगे, पेपर्स भी करने हैं, कल सुबह भी जल्दी उठ के हम लोग करेंगे. Yes, light chapter I know is a very big chapter. We shall be doing that also. ठीक है. वेब सीरीज के लिए देखने के लिए जाते हो तो एक दिन फिजिक्स के लिए जाग ही सकते हो आप. In the night, we talk about light. Okay. Figure 2.16 represents the variation in kinetic energy and potential energy with the height above the ground. The table below represents the kinetic energy K, the potential energy U, and the total energy E of the body of mass M at various heights above the ground during vertically downward and upward motions under gravity. So you can look at this figure 2.16. Now, the table showing the kinetic energy, the potential energy of a body in vertical motion. So, so you look on the screen, zoom करिएगा screen को, and please read this because ये आपको ही read करना पड़ेगा. It is clear that at the ground, that is at point C, H is equal to 0. Potential energy is equal to 0. Kinetic energy is equal to mgh. At the middle point B, x is equal to half h. Potential energy is equal to half mgh. Kinetic energy is equal to half mgh. At the highest point A, that is at height h, potential energy is equal to mgh and kinetic energy is equal to 0. Now, remember, in these calculations, we have ignored the force of friction between the body and the air. In fact, during the fall, some of the kinetic energy will change into the heat energy due to friction and it will get dissipated in the air. At the ground C, the kinetic energy will be less than mgh. The conservation of mechanical energy is therefore strictly valid only in absence of external forces such as friction due to air, etc., although the total energy of all kinds is always conserved. Coming to the next, that is application of principle of conservation of energy to a simple pendulum. Figure 2.17 shows a simple pendulum suspended from a rigid support O. Its resting position is at A. When it is displaced to one side and then released, it swings from one side to the other, reaching equal distance and equal height on either side. Neglecting the force of friction between the bob and the surrounding air, the motion of the pendulum can easily be explained by applying the principle of conservation of energy as follows. So look at this particular image properly. Now let's understand this. Let A be the resting or mean position of the bob when it has zero potential energy. When the bob of the pendulum is displaced to B from its resting position A, the bob gets raised by a vertical height h, so its potential energy increases by mgh, if m is the mass of the bob. Now, on releasing the bob at B, it moves back from B to A. Its vertical height decreases from h to 0, so its potential energy decreases from mgh to 0, and it gets converted into the kinetic energy, that is, half mv square is equal to mgh. At the point B, the bob acquires a velocity v is equal to root of 2gh, so it moves towards C. At the point C, when the bob raises by a vertical height h above the point A, again it acquires a potential energy mgh and its kinetic energy becomes 0. So the bob momentarily comes to rest at the point C. But due to the force of gravity, the bob moves back from C to A. As the bob swings back from C to A, the potential energy decreases and the kinetic energy increases. At A, that is the mean position, it has its total mechanical energy in the form of kinetic energy and the potential energy is 0. So the bob swings again from A to B to repeat the process. Thus, during the swing, at the extreme positions B and C, the bob has only the potential energy, while at the mean position A, it has only the kinetic energy. At an intermediate position between A and B or between A and C, the bob has both the kinetic energy and potential energy, but the sum of both, that is the total mechanical energy, remains constant throughout the swing. This is strictly true only in vacuum, where there is no force of friction due to air. So please remember, at the mean position, the bob has minimum potential energy. Since we are interested only in the change in potential energy as the bob swings, so we may assume it to be 0 at the mean position. Now these are the examples based on it. Numericals, which was expected to be solved by you. It also has numericals and the MCQs. So I hope you might have done this. Now we also have a plan to solve the practice session, the practice paper. We have done one practice paper. We shall do one practice paper now. Okay, and then or else we can plan up the other way around. We can take up another chapter if you all wish so. So I shall read another chapter and then please stay connected. Within 5 to 10 minutes, we will be back for the live streaming with another chapter. So sona nahi, stay connected. If you're new to the channel, kindly subscribe, hit the bell icon, hit the like button, because I think our efforts are definitely worthy of at least a like. So please, please, please do this and stay connected. We shall connect within few minutes. Thank you so much.